Already? Okay, good. Yeah, so welcome to the Pathway Exploration Seminar for Signal Processing and Communications. I'm Professor Martin Reisslein. I'm professor here in the School of Electrical, Computer and Energy Engineering. I'm giving this presentation for the first time, so please apologize if it's not so super polished. Usually Professor Antonia Papandreou-Sarpopoula, who is our fearless signal processing communications chairperson, is giving a presentation, but she has a conflict today, so I've jumped in and try to give my best to present these slides. So I have to also say I'm a little bit conflicted because I'm a member of this group of signal processing communications. My specialty is more on the communications and more specifically in the communication network side. So I'm a little bit of an outsider almost to this group because I'm more focused on, in my research, on communication protocols, protocol aspects, and not so much on the signal processing. I understand what these other folks are doing, but I'm not doing it directly. I'm more working on protocols. And the other thing is, I'm program chair of computer engineering. And so I will give another presentation like this soon about the computer engineering program. With that said, let's dive in here into signal processing communications. You see here some interesting pictures about hot topics in signal processing, autonomous driving, brain analytics, and then listening, sophisticated audio. So let's pull the next slide to give a bit more insight of what signal processing is. It's really, as you probably know from some introductory courses, a general electrical signal that's being processed, and there are many application areas. One application that's very interesting these days is the biomedical related signals. You could think of heart signals, anything to predict say, an oncoming heart attack. There's also related research on neurological signals to predict epilepsy, seizures, and things of that sort. So it's about signals that travel in a system, and you analyze those to make useful inferences and decisions about what to do and how to help the system or help humans in some way. Yeah. So going on a few more interesting application areas, you see here all sorts of signals that are coming from all sorts of systems and sensors, be it weather, structural sensors, health sensors. Then also important here on the bottom right, you have some ultrasonic images, scans in the medical field are very important. And signal processing looks for basically to get the underlying message from this information that's buried in these signals. So there's some noise involved, and you're trying to figure out what is really going on. What can you glean? What insights can you glean from these signals? Yeah? So if you go on, that's no more my corner. That's the communications. So in wireless communications, as you probably all have this running at home, you have an internet connection coming into your house, and then you run a wireless access point, and you wirelessly connect your devices at home. More broadly speaking, this connects then your wireless router connects to the internet, on which then various protocols run to make the overall internet services work, and that's what my personal research focuses on. Related topics are satellite communications underwater. In this context, also becomes very important these days to look at the merging of computation, which also includes signal processing, communication, and storage. So what we are seeing pushed by the big corporation, and you probably know the usual suspects, Google, Amazon, and so on, are pushing their resources, communication, computation, storage, out to the edge of the network. So that's the reason why the various streaming services have improved over the past decade, is that these storage and computation resources are being brought very close in your neighborhoods. So it's not a remote data center that's somewhere sitting at the bottom of the ocean, maybe, to be cool to provide your streaming services, but rather these servers are very close to your neighborhood, and they have a very tight response times, and that's why streaming has improved so much. And so a lot of the work in this area is about improving the layout of the resources and understanding where services are needed and what resources have to be provided. Good. Any questions so far? Actually, where's the? I don't even see the chat now. I think we're sharing like this, unless I somehow figure out. In any case, if there are any questions, don't be shy also to jump in. Oh, another thing that's important is the smart grid that's shown here. So networks gives both communication networks as well as a network for power. So solar is very important. How to control power flows in networks. In the smart grid really is a merged power and communications grid. The smart meters will feed back from the house. Oh yeah, it's good. Can you still hear me? Is everything good?
Yeah, we can hear you, Dr. Reisslein.
Okay, good. Everything okay. Yeah, my wife is just telling me an internet outage. Apparently, I'm good. So, see, lucky so far. Okay, let's keep going. Okay, good. So we'll keep going as long as the internet works here. See, network reliability, also a very important topic. Good. So let's go on. Oh, a new initiative you have also at ASU is that the arts and media. So this is very interesting. If you think of arts performances, say dance or music, a lot of signals involved, and merging now science, technology, and the arts is an interesting area. And ASU is a world leader in that. Sketch the topics that we are dealing with in signal processing communications very broadly. And any questions so far?
Nothing in the chat so far, just one student saying he can hear you. Okay.
Good. Okay, so this slide now shows the faculty, the professors that are active in the signal processing communications area. And you may wonder about the colors, and I wondered too when I first got the slides, but then I kind of correlated. So the blue colors, the blue font, these are our female faculty. And what Antonia usually tries to emphasize here is that in signal processing communications, we are quite lucky to have a reasonably, actually disproportionately high than usual participation of female faculty. So even though you may think of signal processing communications being a very old-fashioned traditional discipline with a high gender imbalance, we do have high proportion of female faculty, and so it's a very diverse group. And we welcome you being diverse students coming into the group and participating in this endeavor. Any questions on our faculty, anybody? Also, you see here a wide range of topics covered. Essentially, I like to say that if you look around to other universities, we are at ASU lucky to have one of the largest groups. And no matter what your specialty is, you will find a world-leading expert in that very fine-grained topic. Yeah? I personally have to say, I did my PhD at UPenn, University of Pennsylvania, fine university, of course. But the drawback at these classical universities in the Ivy League is that they have fine professors, of course, but it's a very small select group of faculty there. And so the topics that they cover in depth, but there's large gaps in coverage areas in between those topic areas. Yeah? So if you align with a particular topic and a particular professor at MIT or Yale or Princeton very well, perfect. But if you're looking for a topic that's kind of outside what they cover there, at ASU for surely will cover it, plus we'll cover everything in between. And with technology moving so fast, ASU is very adaptable and very fast in covering all these topics and all their fine-grained facets completely. And this fine-grained coverage of all the topics also facilitates collaborations across the disciplines, because at other universities, the areas are so far apart that professors have trouble talking to each other because the terminology is so different, there's different subdisciplines. We don't have this problem here. We have enough coverage of all the fine-grained aspects, so everybody can kind of find a collaboration partner in research, and so we can move forward on those fine-grained areas, but with collaborations across some finer-grained topics. Good. I hope I'm not digressing too much here. Going on then, so a few like professional fields you can go into from signal processing communications. Yeah, and as you see on the slides here, a classical DSP, radar are important topics. I also have to say that we have a lot of success in placing students in also the IT chip area. If you think of the Qualcomm, Intel, all the big semiconductor companies, they are under a lot of pressure to integrate signal processing communications into the chip design. Many of the modern chip designs are specialized, or they have general purpose processors, but to make these general purpose processors now work well for the special DSP network function or whatever computing functions you need processing, and to be competitive in that specific space, you need accelerators. And these accelerators have to be prototyped and tailored for specific applications. So at Intel and all the big manufacturers, they have DSP and as a specific signal processing and network function engineers working to develop accelerators or acceleration modules that they plug onto the general processing units to speed them up and make them competitive for the world market. Yeah, so it's really, it's coming together, the merging of the signal processing, communication, computation, storage. It's all happening on the same chip with specialized modules that are all collaborating very closely. Yeah, so it's a very fertile field. It's very active. Yeah. Good. Any questions here? Concerns?
Martin, this is Bob. I do hear from students from time to time interest in this this algorithm development part of that, and some students might not understand kind of the confluence of that sort of code development, algorithm development, and electrical engineering. If you have any thoughts on that, that could be helpful for students.
Oh, sure. Okay. Now, maybe this goes a little bit in the computer engineering field. So what you do need to understand is that the hardware side is important, and especially on those chips that what is semiconductor companies are building. They try to fuse all the high performance modules into hardware that executes something. But what is this something? It really has to be an algorithm. So as you come in as an electrical engineer, you do need to have some basic understanding of how to port or transfer or infuse whatever signal processing you have to do into an algorithm, and that algorithm that has to be translated into a hardware module or something that's a hybrid between software and hardware. That well, like classical EE is alive and well, and there is a trend towards this merging of disciplines where algorithms and the hardware that executes the algorithms come together. Yeah? So if you don't like programming too much, it's kind of getting harder because we do need a little bit of programming software understanding to make the hardware better. Yeah? Because at the very competitive edge, in the world-leading technology, you need to understand both the coding side of it and how the coding is executed in hardware. Yeah.
Thank you, Martin.
Yeah.
There's a related question to this. I expected there would be. That's why I interrupted. So, and so Colton is asking in the chat, in your experience, which programming languages or hardware description languages are most commonly used in SP algorithm development?
Oh, that's a good question. I'm not that so deep into the specifics of this. I believe various companies have their own flavors of various hardware description languages, HDL, VHDL, and so I would just be open-minded. I think the key is studying at ASU here that you take basic courses, or one basic course at least, in say data structures, algorithms also. So venture out of electrical and maybe go over to computer science to get at least a basic data structure course under your belt. And with basic data structures and algorithms, you should be able, and with the VLSI background that you acquire from our EE courses, you should be well equipped and to go into any flavor of HDL or thereof that you will encounter. Yeah. So I think I would also push it for the lifelong learner concept that if you have the basics, you'll be able to flexibly acquire any language that comes along. And from my graduates, I've seen that if they have grasped the basics, they can go on into any specific software or tool very, very quickly, very efficiently.
Thank you. I'll put some of those basic courses in the chat so the students can reference those. Thank you.
Yeah. And I think also the new collaboration ASU has with various industry partners, right? We have looked at this recently with industry modules. Those could be used to, I'm not sure how far this is along now with these. So there are developments at ASU on the way to partner with industry partners to make industry course modules available to students. I'm not sure this is mostly for grad students at this point, I believe, right? But there are efforts underway at ASU to tie the industry tools into the courses here at ASU. I think maybe more for the graduate programs. Yeah. Yeah. Any other questions here, concerns? No. So if you're all good, let's go on. Oh yeah, so here basically list of employers. So you see here typical signal processing, communications type of companies. Also would like to add here that we have also it's a Google, Amazon, maybe missing here, and otherwise it's a fairly good list. Okay, any questions? No. Good. Then let's maybe dive into a few of the courses. So in the junior level, signals and systems 1 and 2 are your basic introductory courses. Then random signal theory is very important. That's the pathway course essentially into the field. It's essentially a way of looking at the world from a probabilistic perspective and how we represent everything around us in a probabilistic way in signals. Many of the signals you deal with are random, because if everything were predetermined, we know everything, we don't have to process. It's the new stuff there, the unknown stuff that's interesting that we're looking for in the signals. So these are the basic junior level courses. Then it goes on to the more advanced senior level courses, signal processing, communication systems. I personally teach the communication networks, the 459 typically. There's also real-time TSP, which is more into the fast processing, becomes very important now with autonomous vehicles. The 5G revolution will bring a lot of low latency processing to the forefront. Then going on, there are many graduate level classes that specialize in particular topics that you see listed here. Also want to highlight that the EEE 554, which is somewhere in the middle here, the random signal theory, that's a core course for computer engineering, and is also a core kind of prerequisite for many of the other specialized courses on signal processing. So the 554 is a key course here. Good. Any questions here, concerns?
There's one question in the chat that is, Can you quickly explain the difference between EE 404 and EE 407?
I'm wondering if Dr. Reisslein's internet outage caught up with him. Uh-oh, sorry, buddy. It looks like we may have lost Dr. Reisslein for a moment. Let's see if he can sneak back in. We've made it this far without much outages like these. Maybe you guys are more experienced with them than we are. Oh, I think he's back. You're muted, Dr. Reisslein. I think you're back though.
So I did get kicked out eventually, I guess. So I'm sorry about that. I hope we are back. And we were on the slide for graduate classes, right? Did you capture the start of this? Yeah. Are we still sharing the screen, or where are we now?
I don't see the screen being shared right now. I think.
Oops. So let me relaunch that. Where is everything? Okay, here is the here is the let me where is the oh, I have to start this from here. Okay, sorry about that. So
and actually, we were just reading a couple of questions to you that popped in the chat. Can I read this to you now? Is that okay?
Yes, let me just try to, where's the slides? Let me see, is this, where's the sharing now? Can I share? Let's see. Okay. Yeah, so go ahead.
Yes. Yeah, Kevin was asking for a brief explanation of the difference between EEE 404 and 407, if you have any thoughts on that. I think that was on the previous slide.
404 and 407. Okay, so do you see the slide now, is it?
Yes.
Yeah, okay. So 407 is the basic introductory course generally to the signal processing area. And it's maybe a little bit confusing that the 404 has a lower number than the 407. I would really view the 407 kind of as a more basic course, and the 404 as a subsequent course that specializes and tilts the signal processing more towards the real time. Yeah. And so I would recommend, if possible in your program of study, to first take 407 and then take 404, or you could take both of them at the same time. However, that being said, I believe it's possible to take 404 also without 407 as a prerequisite. Is it possible formally?
I believe so.
Yeah, and the reason for this is that in 404, you do get an introduction to the basics of signal processing, not in as much depth as in 407, but then the course takes a turn more towards the implications for practical implementation in a real-time sense with low latencies. Yeah, so it's more about the processing specifically on embedded hardware. Whereas in 407, you don't worry about how it's computed. You learn the general concepts. Yeah. So 404 does get a bit more into this, how it's computed, and this merging of the signal processing, the algorithm, and the computing in hardware implementation. Yeah.
Thank you. And there's one other quick question was, Colton is asking, are Kalman filters covered in any of the undergraduate signal processing courses from your?
That I honestly do not know. I'm sorry.
No problem. The student.
I would speculate not too much, maybe a little bit. See, Kalman filtering comes in more we have the Professor Scaglione and Lalitha Sakar in their courses. They are the experts. And looking here, I believe if you take the grad class, here is the second from the bottom, statistical machine learning from theory to algorithms. That I think is by Professor Anna Scaglione. I think she does a lot of Kalman filtering and related things in the statistical machine learning course. Then also when you take 1, 2, 3, 4, the fourth from the top, deep learning, media processing, understanding, that will go into the deep learning, Q-learning, reinforcement learning type of, and the Kalman filtering as an instantiation thereof in the signal processing space kind of topic. Yeah. But generally, again, I wouldn't get caught up too much on specific Kalman filtering, but again, keep an open mind, and that's what those courses will teach you, to look at the broad field and look at all the options that are there to explore this general concept of prediction, learning, deep learning, and how to do this efficiently in a wider context. Yeah. Does this make sense?
Yeah, you got a thank you from Colton. Thanks.
Okay, sure. You're welcome. Good. Then next slide. This is about grad school here real quick. So the signal processing communications field is rapidly advancing, as I've tried to point out, and there's increasingly a push to hire graduates from graduate programs. Yeah. So having a master's or PhD is quite common in these areas. So having an undergrad degree is good, but many companies do look for masters. So if you're interested in a 4+1, it does pay off. And I have many PhD graduates traditionally went mostly to academia, but in recent years there's been a strong push by industry to hire PhD graduates, especially for their development, researchy type of positions. It is almost a requirement to have at least a master's and preferably a PhD. And as pointed out here, it's not only academia, it's the labs and also many companies that are, if you have to look at these very advanced topics, and if you want to be a world leader in any of these, you do need to bring many disciplines together, and PhDs are so much stronger in maintaining that. Yeah. So good. So we are almost through here. So if any questions at this point?
No more questions at this point.
Okay. So I also may point out here that it's important, the direct PhD is important. I want to point out here that in our program in electrical engineering, you can go from the master's onwards to the PhD quite seamlessly. Also want to point out here that in our computer engineering program, we have a strong research focus. You can take many so-called reading and conference courses that are specialized and tailored to your specific research to advance and fulfill the course requirements for the PhD. So you can dive into your research topic very early, and there is then faculty who are looking for research assistants. So you can hope most PhD students get their PhD studies fully paid all the way through. So it can work very, very seamlessly then. Any questions?
There is a question about, Claire is asking about the Dean's Fellowship. Do you have any comments on the Dean's Fellowship in general, Lynn or Martin?
Not really.
Aren't
you the expert, or is Lynn the expert for this fellowship?
We'll let Lynn handle it. She's the best. She's the expert.
Perfect. Thank you.
So Claire, that's a great question. The Dean's Fellowship is a highly competitive fellowship that pays for your tuition and health insurance for 4 years in your PhD program. It also has a stipend of $30,000, which is more than what the average RA or TA receives as a stipend. So the Dean's Fellowship is only available for domestic students, and we have a very limited number of them, so it's highly competitive. So the higher the GPA, the better. If you're talking to a faculty member about a PhD program and you are interested in the Dean's Fellowship, you should definitely let them know, because they have to provide 50% of the funding over the 4 years. So they do have to be able to provide funding as well. So when you are speaking to faculty about PhD programs, it is common for you to speak to them about funding opportunities. It's a big decision for you and for them. And I know it can be a little awkward talking about money sometimes, but you just have to do it.
Yes, I mean, also to reinforce what Lynn said, it's in a sense a business transaction, right? Faculty have research projects that are externally funded, and looking for, in a sense, employees, I almost say, to carry out the research tasks, and the PhD students are the employees. Yeah. Now I know in the US here it's a little bit more awkward. I also collaborate with universities in Germany, or in Europe generally, in Germany especially. The PhD student there is viewed as a regular employee. I mean, they don't say you're a PhD student. They say you are a scientist, yeah, that is employed at the university, and they are like in the regular system, like an employee. The PhD student nature of it is kind of secondary. But they view themselves all as employed scientists. And that is also factually the same thing here. From most PhD students are, in a sense, employed scientists being employed by that faculty who is conducting research on an area with external funding and needs to carry out this research. And the good thing now here is in the US, in contrast to Germany, in Germany you usually work on some other topic, and then you research it somewhere else, and so you have to work twice. Here in the US, our externally funded projects are usually very closely tied to original research that you can publish and build your PhD on. Versus in Europe, many of the projects are very applied, very broad, and it's difficult to extract a PhD thesis from that, or it takes extra effort. Versus here, if you do work on such an external research project, you can directly copy over your results into the PhD thesis, and you're done. So it's very efficient process, and you are essentially an employee, an employed scientist at this in this research group. Yeah.
Thanks very much.
Yeah. Any other questions, concerns? Signal processing, communications, networking. And again, I want to emphasize here that it's a good field, but look at it broadly. Electrical engineering is highly interdisciplinary. So you may be in antennas or radio waves and propagation, but these antenna signals need to be processed, and there's software radio where essentially the antenna signals are processed by DSP chips. So it all comes together in the end. Even the circuits field, right? Circuits implement whatever signal processing algorithms we have. You have to implement in the circuit. So it all comes together, and we need to have the broad perspective on all these topics. So don't only go down the rabbit hole of only signal processing communications, but keep a broad mind of those related areas that you will need to make it all work in the end in a technology or product.
Martin, there is one additional question. Maybe we'll entertain one more of the graduate school ones, but we'll put a plug in for the graduate school pathway for the next one. But why don't we take this one too? There's a student asking how many PhD students that you're aware of that actually complete in 4 years. I know that's very subjective, but
I think we were just discussing in the faculty meeting last week, right? That I think the average was 4.5 years.
So the average completion rate for our PhD students is currently 4.9 951 years.
Oh, okay.
We do have some PhD students that are working in the industry and are doing PhD part-time, and they do take longer. So that is what is, pushing us towards the higher end of 4 years. I would say 4.5 years is standard for our students that go from bachelor's into PhD. You're going to be taking coursework very quickly and working on your research very quickly. But you will have a leg up because you'll have already taken all of our undergraduate level classes. And like the slides earlier were showing with our graduate level classes, you don't need to take the 591 component. You can jump straight into other graduate level classes.
Yeah. And maybe to add on here, so that there are, I know students myself that managed a PhD in 2.5 years. So if you're really on top of it and are lucky, there's a little bit of luck involved, right? Because you need to find a research topic and you need to make progress and publish in this research topic. And sometimes the topic is you can just get lucky picking the topic, your results come out well, but it's a little bit of risk involved because it's you venture into the unknown and you don't know what you find. You may find nothing and then you have to iterate until you find something, or you may find.
I think you just got muted, Martin. Oh, there you are.
Okay. So it's a little bit of like venturing into the unknown, and you get lucky or a little bit unlucky. So if you do get lucky and things move quickly, you can get through in 2.5, 3 years if you do it full time. And this average is skewed up also because there are, as Lynn mentioned, part-time students, and I've students have myself that work full-time in industry, have very demanding careers and do the PhD on the side. And there's no surprise that it takes 5, 6, 7 years to complete a PhD because they're doing their full-time day job, and then in the evening and at night they are doing a little bit of research also then to complete a PhD research. So it's the 4.95 or whatever it is, maybe a little bit misleading. If you, it depends. If you do work full time, it can be quite fast here.
And we can talk more about it at the graduate pathway. Cheryl, can you remind me when that is? Oh, you're muted.
No, Cheryl's muted. Okay.
It's in about a month and it's going to be on March 10th.
Awesome. So everybody come on March 10th. We'll be talking more about grad school, but one thing that you can do now to ensure that if you are thinking of graduate school, thesis, or PhD, and you want to go quickly through it, so either the 4+1 thesis program or direct PhD, get involved in research now. Really figure out what it is you like and what you want to do, and you're going to enter grad school ahead of everyone else.
Yes. It's really the PhD is a research degree, like first and foremost. So the coursework is there, but it's a little bit of a nuisance almost, or it will prepare you for some aspects of the research you're doing, of course. So you do need to take some courses in to get the tools under your belt that you need to do your research. But then you really have to go out and do your original research with a faculty advisor, which is usually a close collaboration. And so that research, that pushing the envelope of what's known, what science we know, that is what the PhD is about. And this is the big unknown with the timing factor. It can go very fast, or it can become a bit tedious if you get bogged down somewhere. That is where the unknown comes in.
Thank you. And while we don't have other questions at the moment, but I'm going to put in the chat, students, I'm going to put in a link for faculty by research area to kind of back off what Lynn and Dr. Reisslein are saying. Is the best way to get to know about this is to identify faculty who have shared interests with you. And you can read about them here, and it's not strange for you to email those faculty and maybe even ask for an informational interview with them to discuss what they do. That's often the best way to get started. And the other reason, if you click on the signals area in that link, you'll see back when at the beginning of the presentation, we do have some very wide range of signals faculty doing very interesting, fascinating, industry connected and research connected things. So please read those links. Whenever we do these pathways, we want you to know more about our faculty. We have some faculty do some real cool things. So that's in the chat. Are there any other questions at the moment? We may be at the end here, Dr. But thank you very much, Dr. Reisslein, it's awesome when we go off topic a little bit, because that really gives students a insight into what it is you guys actually do. That's often a mystery, especially to our undergraduate students in a seminar like this. They often don't know much about our faculty. So thanks for filling in some of those mysterious gaps.
I hope I didn't digress too much. Sometimes
no, it's fantastic.
It was very good.
Okay.
That's the stuff
right.
that's the stuff that we want these seminars to do. So thank you for going wherever it needed to go.
Yes, thank you so much.
No signals were crossed.
Oh God, Bob, please stop.
Okay, well, I think we're getting some radio silence now. So maybe we'll just stop it. So Colton thanked us for the link. So again, thank you for your time. I think we're getting some thank yous in the chat to you, Dr. Reisslein. So thank you for taking the time. I know you're busy, so thanks for taking the time to do this.
Yes.
Okay, good. Okay, thanks. Then see you in March then for the graduate programs and computer engineering. Yeah.
Yes, thank you.
Everyone's thanking you, so it went very well. Thanks very much.
Bye.